Okay, I think we're good to get started again, everyone. My name's Liz Ferguson. I work for Wiley, and as Mark said earlier, I'm on the organising committee of the COASP meeting. It's my pleasure to introduce the technology and innovation speakers for our first panel discussion this year. I'm going to start by saying we've got a slight change to the program, so the updated version is up here. Tiffany from Standard Analytics couldn't join us, but we're very lucky to have Alberto Pepe join us from Authorea, and he's going to talk about from open access to open science and why the future of the paper will be data-driven.
All right. Let me get back to that. All right, so I guess since I have 20 minutes, I'll just start with a very brief introduction about myself. So I started working with open access about 12 years ago when I was working at CERN, and I think that there's someone from CERN here. Oh, sorry. Is that better? All right. So I started working on open access about 12 years ago when I was selected to be part of a task force for open access at CERN. And I think that there's someone from CERN here, and yes, you don't know me because you're too young. I'm actually not that young. I was working there 12 years ago, and it was a very interesting task force. We were promoting open access among particle physicists, and we're working with publishers to ensure that all the work that comes out of CERN is open access. I think open access is a great idea, but I think that exchanging PDFs is great, but we can do better than that. So in the last 10 years, I've been more and more interested in open science, which is the idea that not only the PDFs, so the superficial layer of science needs to be open, but also everything that exists beyond the PDF. So what I'll talk about is pretty much the motivation behind some of the projects that I've been working on in the last few years. And I always start my presentations with this one slide that pretty much sums up all the frustrations that led to me leaving academia a couple of years ago and starting a project called Authorea. So this pretty much sums up my feeling about how science and scholarship is being conducted these days. So as a scientist myself, I think that the work that is produced by scientists is cutting edge, so it's 21st century by definition because it's novel, original, it's all new stuff. But when you look at the tools that scientists are using today to write up research, it's things like LaTeX and Microsoft Word. These are tools that were designed in the 1980s, and they were really intended to be used by single person working offline. And now we're working together more and more, and we're working online. So we haven't really adapted the tools that we use to the sort of the web and the new way of doing things. But what really makes me angry is the fact that we're still packaging all the work that we do as scientists in a format that is 400 years old. If you look at that paper over there, which is roughly 350 years old, that paper actually doesn't look too different from what we publish today. And I think that that's a big problem. So one of the reasons that I started off working on a project that is all about authorship, and it's called Authorea, is because I think that in order to change publishing, so the final, what we end up publishing at the end, we need to start by changing how authors are producing the content. But going back to the paper there for a second, you see the 350 years old paper. Let's take another step back 50 years more and go to the very first paper published, or one of the very first papers published by Galileo. It's one of the most famous papers in science, and it's one of the papers by which Galileo pretty much discovered 4 planets orbiting Jupiter, and it's a foundational paper in astronomy and sort of the observational evidence of a heliocentric solar system. So as you can see, that's the front page. We don't publish front pages like that in most journals anymore. But if you look inside the paper, what you'll see that Galileo actually used a very interesting way to describe his work. So what he's saying is producing a very narrative account of what all the steps that he was taking in order to observe his results. So as you can see in the diagrams, for example, you can see the position of Jupiter, and then the little asterisks are the position of the stars, so the planets around Jupiter, and he records how they move around the planet. If you look at the actual text, he uses plain English. Well, the original one was not written in English, but it's very easy to understand. There's a lot of metadata. I was, for example, sitting in my backyard, pointing the telescope in this position. It was that time of the day, so there's a lot of metadata. So what we can learn here is that Galileo actually had a very narrative, personal, subjective way of describing his work. But what's even more interesting to me, I think, is that he's publishing all the data that he collected. So he's not producing some high-level analysis, I don't know, principal component analysis, and just publishing the results of his work as a JPEG, like we do today. But what he's actually publishing is all the data he collected. And in that case, he was looking through a telescope, annotating on a notebook the little circles and the asterisks, and that's everything he published. So what's important here is that all the raw data that he collected, together with a lot of annotations, were published. That's the idea of publication for Galileo in one of the very first papers published. So the problem is that we don't do that anymore today. The data has become a lot larger. Most times, oftentimes it just doesn't fit in the paper anymore. So we end up reducing it, analyzing it. We produce a nice graph, and we end up publishing that graph. And everything else we've done, the data, the code that we wrote, is entirely lost. And that's really bad for transparency, reproducibility, but also to really allow other people to build on top of your work. So still, we're using this system to publish science. So my question to you is, if we had a younger Galileo, maybe hipster with some like Ray-Ban glasses, if he was around today and he had to rethink scientific publishing, what would he do? Like, what are the steps that he would take to share his results with the world if the results don't fit anymore in a piece of paper? So that's roughly the foundation of the motivation and inspiration that led me to create a project and do something about open science and, in general, scientific transparency, and the idea of a paper of the future, which is data-driven. So that it's not just a piece of paper, nicely formatted, but a paper that really contains also the data, the code, and all the different materials that are necessary to reproduce or just simply analyze an experiment. So when I give this talk to astronomers, they always say, well, but we link all the data sources in our papers. So if you just look at our papers, we have data links that point to the data. And my answer is always the same: that's not enough. And I show them this study that I actually conducted with some people when I was at the Center for Astrophysics at Harvard until a couple of years ago. This is a study looking at all the astronomical literature. So we actually analyzed every single paper published in astronomy between 1997 and 2008. So roughly 10 years of data here. And we looked at links to data. So as you can see, in 1997, that's the very first days of the web. And in astronomy, you already started seeing a couple dozen links in the literature, and then the number increased over time. And some of the data at the end, there's some missing data, but it's going up and up. And so every bar represents the number of links that we found in papers. And then the green part of the bar is the links that still work today. The gray part is links that don't work. So what you can see here is that roughly 7 to 8 years after publication of a paper, 50% of the links in papers just point to nothing. They're dead. That's worrying, right? I mean, honestly, that number should be 0 every year. If we think that data linking is the best way to support for data to travel and to be disseminated around, that number should be 0. Even if it was 1%, it would be a problem, because 1% of all astronomical research is pretty much lost. But that's not even 1%. It's like 44%. That's like half of the literature cannot be reproduced because we don't have links to data anymore. So that's bad. With a group of people, includes some more people, but it's roughly like my crew at Harvard. So we started thinking about the paper of the future. The idea here is to really try and reinvent the scholarly article. We've linked, up to now, we still circulate and disseminate articles that look like a piece of paper, but we thought that the paper of the future maybe can be something a little more than that. And as we wrote this paper called The Paper of the Future, and the idea is that our attempt was to try and integrate as many rich media as possible inside the paper. So what we say here in bold towards the bottom of the paper, the short article explains and shows with demonstrations how scholarly papers can morph into long-lasting, rich records of scientific discourse, enriched with deep data, code, interactive figures, audio, video, and commenting. So the thing is, in order to write the paper of the future, we also had to build a platform that would allow for such papers to actually exist. And that pretty much was the foundation and the inspiration, and gave me like the initial trigger for creating a project that pretty much would allow all these data sources, whether it's data, code, video, audio, commenting, annotations, to exist in a new format. And the new format, actually, we didn't have to think very long. It's just HTML, because that's the language that we all use every day when we're in front of our computers. So, moving away from PDF, moving away from Word, they're just formats that you can export to, but the main language that we use is just simply HTML. So as I said, that's the motivation behind Authorea, which is a tool that I'm not going to demo, because I'm not going to just talk about the product itself. If you like, you can talk to me after. I can tell you a little bit more about the platform. But what I want to talk about is some of the features that we've been building to make sure that we have a platform that allows authors to write in a different way. And the different way that we think about is online first, so web first. So every single thing that they produces a version that exists on the web. And it's really a new way to write research that is really putting the author first. So we're producing a lot of features that make authors' life a lot easier. So I'm going to talk about some of the stuff we've been working on and some of the sort of decisions that we had to make, also from a technical perspective, which I think are interesting to the community of publishers. So the first thing that we wanted to solve when we said, hey, we're going to create a tool for authors, we said, what's the most pressing problem for a lot of authors? Well, I'm an astronomer. I worked at CERN, so I've seen papers with hundreds of authors. I mean, you've seen that. The first 3-4 pages are just author names. So the first problem we wanted to solve is let's build something that is collaborative natively, that we don't have to build a collaborative layer on top. It's just collaborative from the beginning. So the first problem we wanted to solve is versioning, so allow multiple people to truly work on the same thing together. If you've written a paper, I am sure that you've used a file name like that. If there's not 2 or 3 finals, then it means that it's not a very final version. It seems like you count how final the version is by the number of times you say the word final on the file name. So how did we actually solve that? We built the entire system on a version control system called Git. Git, maybe some of you know it, some of you don't know it. It's a version control system for source code, so it allows multiple developers, engineers to work together on the same piece of code. It was not built for documents. What we're doing, and what we did, is that we're repurposing Git to work on documents. So we do track changes, not as a layer on top of like an editor, but it's native, it's inside the content itself, which I think is pretty cool. We're about to roll out a new version of the editor that allows you to do track changes just like that. So if I write a word, this is an awful article, and then Josh removes awful and replaces it with amazing, then I will see, if I'm the owner of the article and I have suggestions on, then I will see something like that where I can accept or reject And I can see every single thing that changed in an article between 2 different days. I can roll back at any point in time. I can undo one change that happened 100 days ago instead of having to click undo 1 million times to get to 100 days ago. So the idea is to really make the entire process of track changes a lot smoother. But the whole point here is that we're not just an editor. We don't want to allow authors to just write. We also want to allow them to deposit data. So this is an example of a successful story that we had on Authorea. It's one of the first epidemiology papers that covered the outbreak of Ebola in Africa from about 1.5 years ago, 2 years ago. And a group of researchers at the Broad Institute used Authorea to write the paper. And then the great thing here is that they published their article in Cell. So they got, of course, their they had to publish in a high-end journal because this was top level and high impact research. However, at the same time, they have an open version of their article, and the version of the article has a folder view, which is essentially the Git repository behind, that contains all the data for the article. So the great thing here is that anybody can go to the Cell version, and at the bottom, there's a link to this version that actually contains not just the paper, but also all the data associated with it, which I think is great. And then we do something that is a little more than just data support. We also allow interactive graphics. So things like this, we wrote a blog post a couple of days ago looking at, imagining if research was an Olympic sport, how would countries rank? So we wrote a blog post that you can find online, and we actually published a very interesting graphic, its medals won by countries versus their publication output. And it's an interesting blog post if you'd like to read it. And then next to it, there's a CartoDB map that we made looking at tornadoes in the United States. And again, it's a map that you can play with, as you can see. So you can just allow, play with the data inside the browser. So this is the sort of stuff, Jupyter Notebooks, D3JS, Plotly, CartoDB, and any other sort of plotting library that authors use. That's the sort of stuff that we, as the producer of an authoring platform, would love to see published by you. That's the sort of stuff that we love doing. And it's not because we love fancy graphics, it's because authors, they're already producing these great visualizations, and they want to see them published, because I think that an interactive way to look at graphics like that, to look at data, is more interesting than a static one. Just a couple of other things that I'll talk about. First of all, I've had the pain myself of, since I worked at CERN and then I was in physics and astrophysics, I mostly use LaTeX, this terrible beast that probably not many people know about, but it's a huge pain to work in LaTeX, especially when your supervisor, for example, doesn't want to work in LaTeX. So you end up writing your paper in LaTeX and then exporting to PDF, sending to the supervisor, who will print the PDF and send you comments handwritten, and then you have to convert them into LaTeX once again. So I felt the pain myself of different formats and entirely different communities and paradigms that exist in science. LaTeX is pretty much unknown in the life sciences, and it's bad that there's two separate poles in a way, that the guys using Word, the guys using LaTeX. Now more and more people using Google Docs, which again is great, but it's not really built for scholarship. So we decided to use HTML as a way to let everybody talk. And since we're really author-centric, we're also trying to develop features that allow authors submit to publishers. We now have more than 8,000 styles that you can just sort of write your paper and then in one click export your paper in Word or PDF and send it to the publisher. Maybe one day we'll be able to give the HTML or XML straight to the publisher. That would be great. And the reason that the number 8269 is going up is that we actually allow people to build their own styles. So we're open sourcing the styling and exporter so that anybody can build new styles and allow direct submission and formatting to publishers. Just a couple more things. We're also all about, of course, openness and data sharing. So we're starting to build some metrics so that authors, 1 minute, okay, I'm done. So that authors also have a way to track and how many of their papers, for example, have data that is shared and so on and so forth. So this is, of course, a fake account for Marie Curie showing that 61% of her research is open. And then the last one, since I'm at a publisher conference, I had to show this little meme over here. So I always tell people that, yes, publication times are long. It takes a long time from the moment a paper is submitted until it is accepted. But what we're trying to shorten is not so much the publication time, maybe in the future, but for now we're worried we're worried about the writing and the authoring part of the process. And I think that making authors produce manuscripts much faster will also sort of push you to have much faster publication times. And that's about it. So I'll stop there.
Fantastic.
Thank you.
Terrific. I think our first Oscar goes to Alberto. We'll take questions for the panel at the end, so we'll just move straight on through the talks. And next up, we have Dario from Wikimedia talking about the need for citations.
Thank you, Liz. This works. Okay, brilliant. Hello, everybody. My name is Dario. I run the research team at the Wikimedia Foundation, and today I'm here to talk about some opportunities that I think are really important and not very often talked about in terms of how Wikimedia projects, open knowledge projects really in general, can augment open access and vice versa. And I want to start to talk about some unintended consequences that we discovered while building an encyclopedia, right? Today, as everyone knows, Wikipedia is the largest online reference and it contains content across almost like 300 languages. Not many people know that there are some other key aspects to this project that I think are going to be particularly relevant for this community. So the first one is the fact that Wikipedia has become today a major entry point into the scholarly literature. So it works both as an entry point for discovered literature and as a massive dissemination channel for the literature, both paywalled and open access. And thanks to our friends at Crossref, now we have data to quantify what that means. So we know today that Wikipedia is among the top 10 sources of DOI lookups globally. So it's often orders of magnitude larger than most publisher platforms in terms of like giving people access to the papers that you guys are publishing. We didn't know this until recently, and it blew our mind when we discovered exactly the volume of traffic and visibility that Wikipedia drives to scholarly content. And if we only look at the field of medicine, the best estimates we have today suggest that just the medical content on Wikipedia receives more traffic than some of the top sources. You cannot really see it there, but WebMD and some of the other institutional sources of medical health-related content receive less traffic, less attention than Wikipedia. So we have a responsibility to make sure that the best possible research, the best scholarship makes it to the #1 source that people are looking at when looking for information about diseases and drugs and so on. And even in the context of major public health crisis, Wikipedia offers like I think a very important service, public service, in terms of disseminating information is critical, like in the context of the Ebola outbreak in West Africa, where Wikipedia was the top used internet site in the regions affected by the outbreak. And thanks to our Zero partnerships, we're able to disseminate content and summaries of papers, again, both paywalled and open access, with no data charges to the local population. So I think this gives a sense of what this means in terms of distribution of content, scholarly content for the scholarly community. But there's also another area that is really very rarely talked about, and it's basically Wikipedia for robots and machines. So Wikipedia, if you're using today any semantic search system, any knowledge graph that powers any of the major platforms you're using on a daily basis, there's a very high chance that all the semantic data that powers it comes from Wikipedia. And in fact, if you look at the map of it's completely unreadable, I'm sorry about this. You find the slides later. If you look at the map of what Wikipedia represents in the context of this ecosystem, it's the highest centrality node in terms of providing data to this ecosystem. And this is only about the linked open data ecosystem that is public. There's much more usage of Wikipedia data that goes into proprietary platforms like Google's Knowledge Graph, Apple, Netflix, you name it. And the way in which this works is that there's this project called DBpedia. I don't know how many of you have heard of it. DBpedia takes the entire giant content dumps that we generate and using algorithms turns these dumps into a set of RDFs. And basically this linked open data is then propagated to the entire linked open data ecosystem. There are some challenges with this model. The first challenge is that when we talk about citations in Wikipedia, it's ironic that possibly the most important ingredient of a Wikipedia article, a citation, is still supported by a very brittle mechanism. Basically, citations are blurbs of text embedded in a Wikipedia article. There's nothing like a reference management system or a bibliographic database in Wikipedia as of today. And when it comes to the conversion of content into RDFs, also that process is not optimal because like I said, the generation of this giant linked open data repository is done by machines. So there's very little quality control that involves human beings and experts and curators in the process of generating this data. So the question then becomes not just how to build a comprehensive online encyclopedia, but how to build a knowledge base that A, is machine readable and complies with the standards that are set in the linked open data community, that is designed to be editable by anyone, so experts and lay people alike, volunteers and professionals, machines and humans, that it expands the scope beyond those entities that already exist in Wikipedia to basically become the central place where you can find information about anything you can name virtually. And finally, and most importantly, how to make sure that this knowledge base also supports transparent verifiability via citations. So today we have a project that allows the creation of a human and machine readable and writable open knowledge base. It's called Wikidata. And I want to talk about it a little bit today and also give you a sense of how you can contribute and leverage this platform for supporting open access. Quick show of hands, how many of you have heard of Wikidata before? Okay, awesome, fantastic. So in a nutshell, Wikidata is really Wikipedia applied to structured data. So it's a free open knowledge base that anyone can edit. It works pretty much as Wikipedia, revision controlled, distributed using open licenses. It was launched in 2012. And it's fully integrated with Wikipedia and our other sister projects, meaning that it comes with all the scalability, persistence, branding, licensing scheme as any other Wikimedia project. As of this month, we have about 20 million items in Wikidata and about 100 million statements. And it's currently the fastest growing project we have. So it's still not as large as English Wikipedia, which has the largest active contributor population, but it's definitely one of the fastest growing ones among our ecosystem. And in a nutshell, Wikidata is just a set of triples, right? So represent that something has some property. And you can also add references and qualifiers, but that's pretty much like the building block of Wikidata. And using these building blocks that we call items and statements, you can basically represent the relation between any two things you can name. And basically, Wikidata allows you to connect information about cities and bacteria and species and pop culture. Basically, it's a giant network of every entity and how it's interconnected. Now, the amazing thing to me of Wikidata is not just the creation and ingestion of this data, but also the APIs that we release so that you can access this data and query this database and see what, discover things that historically have been pretty hard to discover. This is an example of the birthplace of people employed by MIT as extracted from Wikidata. It's using this interface based on Sparkle, the most popular query language for structured data. And it's all generated on the fly. You can follow this link. You will basically be able to generate these maps on the fly with real data that is pulled from Wikidata. And there are many other examples that will be relevant here. I can give you a demo after. This is a map of authors in Wikidata and Wikipedia with a known location, like a birthplace or a residence, and an orchid. Still a lot more to do there. The example that I'm probably most excited about is the GeneWiki community and their efforts to represent on Wikidata a broad range of scientific data. So this is a community in bioinformatics that is basically extracting knowledge from the literature and representing the connections between genes, proteins that encode these genes, diseases that are associated with specific genes, hosts of viruses, et cetera, and all of this is shared, is extracted from the literature using machines and experts alike, and deposited into Wikidata, and then integrated and reused with our broad projects. And the reason why I think this is very exciting is that it's going to allow us for the first time to answer questions that have been really hard to answer just looking in the literature. So for example, getting all drug-to-drug interactions of a specific drug, getting a list of diseases that are known to be treated by a particular drug, or those that, in virtue of their association, might be treated with a given drug. So this is something that I imagine the scholarly publishing system, this is kind of research that the scholarly publishing system should support, but there's no infrastructure as of today that the scholarly publication system is providing to answering these questions. They're all based on data that is part of the contents that this community is publishing. So having this data in Wikidata extracted from literature really makes it possible to answer questions that historically we've never been able to answer. And there's the second part of this project that I think is really important, and that's the ability of represent the provenance of this information and allow, we're talking before about open science, allow this research to be traceable and reproducible as much as possible. So I really like this quote from Egan, who said that in 5 years, the verb to Wikidata will mean to look up a fact with literature provenance. This is particularly important because it will allow us to get close to something that we can consider computable trust. Basically, an idea of like assessing the trustworthiness of specific statements as a function of the reputation of the authors, the reputation of the outlet, the processes that go into producing specific scientific results, et cetera, and all of this is going to be accessible via tools that allow us to query the literature and perform this kind of analysis. So earlier this year, we partnered with Wikimedia Deutschland, and we got support. We were supported by the Sloan Foundation, the Moore Foundation, and Crossref to try and throw some money and effort into this initiative. So basically the idea of creating the first centralized open bibliography repository on Wikidata to serve our entire ecosystem. And what that means practically is actually a set of tasks that are actually quite boring and technical, involving like designing data models, figuring out the data, cleanup workflows, et cetera, But the ultimate goal is really to provide not just a central repository for Wikipedia and Wikidata, but really a central repository for science, for open science, that can leverage this kind of infrastructure. And I want to give you a few highlights of what happened over the past couple of months since we launched this effort. So we have now ingested all the bibliographic metadata and the entire open citation graph for the open access review articles published in the 5 past years as obtained from PubMed. So as you can imagine, having all this data integrated in Wikipedia is a no-brainer. Wikipedia should just leverage all this content and integrate it into its own articles. The second project I'm also very excited about is the creation of a corpus on Sika research. Previous talks mentioned how critical it is and to provide answers that are immediate to some of these biggest public health threats that we're facing as society. And one possible way in which we can do this is by opening up all the data that we have around this corpus of research. It's a pretty small corpus. We're talking about 1,000 papers published so far on Zika virus. And what we're doing is we're working on Wikidata to create this 4-layer data set to like showcase the vision behind this idea. An encyclopedia layer that basically represents the links between Zika-related articles and media files, for example, that we have on Wikipedia. An expert annotation layer, like the one that I mentioned before, curated by experts in the GeneWiki community, where we can represent all these facts extracted from the literature, connecting genes and hosts and diseases and the manifestation of the virus, et cetera, et cetera. A bibliographic metadata layer, where we store all the metadata for these papers in Wikidata itself. And finally, the open citation graph layer. So something that, alas, is still very hard to find outside of proprietary databases. And there are a number of benefits that we can get out of this effort. This is an example of this is just one query that you can run, and it will give you a bubble chart of the most cited authors in the Zika research corpus. And down the line, we hope we'll be able to filter it by journal, OA status, type of statement, et cetera, et cetera. There's also a separate and really exciting area of research and development, which involves the use of algorithms for mining the literature and extracting facts that could become candidates of what we want to have in Wikidata and Wikipedia. The two main efforts in this area are Content Mine, many of you might be familiar with, and Strepit is another project that we're supporting financially. And at a high level, what they do is that they mine the literature and they give us recommendations of triples or statements with sources that we can then recommend to our community to ingest into our projects. So I believe that this is going to be really the future in which, the way in which in the future we create open knowledge by a combination of algorithms and human curation by leveraging really like the rich content that the open access community is producing. And one day, we'll be able to perform queries like the following just by running Sparkle queries using this interface. One problem we currently have is the fact that there might be information in Wikipedia that is based on papers that got retracted. And as you know, the life cycle of a retracted paper is way longer than the retraction itself. So this is particularly critical in the context of Wikipedia. Remember what I said before, where all information that goes into Wikipedia is then propagated into thousands of data consumers, right? Making sure that we can quickly and effectively fix information that has been retracted is really a fundamental goal, not just for Wikipedia, but also for the entire ecosystem. So this will allow us to identify statements citing journal articles that was retracted, for example, or statements citing a source that itself is citing a journal article that was retracted. So given that I didn't come here just for drinks, but also to ask you a number of things, I thought I would give you a list of things that we need to support our projects, and as a result, better support open access. So the first ask is around the open citation data. Everything you've seen here cannot be done by using proprietary citation databases that some institution has to subscribe to. So the only way for these communities, for our volunteers, for these machines to generate, honestly, information that quite literally is saving lives, is to have an open citation graph. So the first ask is please make sure you deposit your citations. There are protocols and best practices. Crossref is the organization you want to talk to. Just releasing this data to Scopus or Web of Science is not going to help this effort. We need really to shift towards a different model when it comes to the value that this data is producing. And second, I mentioned these amazing examples of projects that are scraping the literature and generating potential facts to be ingested into Wikipedia and Wikidata. The only way for this community to do so is by having content that supports mining rights. So licensing and formatting that allows and facilitates content mining is really critical for us to be able to ingest this data and in turn give access to people to the source publications that are behind this content. So I want to finish by saying that my perception as a, consumer of open access is that we should really ditch the idea that the superpower of open access is a citation advantage, or the fact that one day we'll be able to beat closed access publishing. That's not the point. The point is not to beat an antiquated system based on citation-based metrics. The point is to try and figure out ways in which your content, your data, basically this gold mine that you're sitting on, can be leveraged to produce, to support knowledge, and in turn, how that knowledge can feed back into the content that you're producing. So by sharing this data, I believe that we'll be able to accelerate the discoverability of scholarly publications, as well as its reusability and its broader social impact at large. And with that, I'd like to take any questions, or I guess after the third talk.
Yeah, we can take those.
All right.
Perfect timing.
Thank you.
Excellent. We have some time now for questions. Have we got any questions in the room? Everyone's been stunned into silence by the brilliance of the ideas on display. Mark.
So I've just got, I think, a general question that is relevant to all three talks, which is about adoption. So the projects are at kind of different stages. Dario talked about the combination of machine-based sort of curation tools coupled with human curation. Obviously, with Authorea, I'm really curious about how much adoption have you already got? What kind of barriers and challenges are there? These are all, fantastic and exciting ideas. So how do you address that issue of adoption?
Do you want to go first?
You can go first. I have one slide.
It's no secret that if we look at our users, a lot of the users on the platform tend to be younger scientists. So we actually did run a survey asking, doing a bit of a demographic to see how, who's actually using Authorea today, and it turns out that most of the time it's people between 25 and 45 who are mostly in the more computational fields. So whether it's computational biology or computational social science, people that use data, people that are, of course, knowledgeable with with data handling that know about Jupyter notebooks and they know about Git and things like that. Of course, that's a problem because the moment that they actually invite their professors or advisors or simply colleagues and that are used to a more traditional writing workflow, then that's the barrier. And that's the problem. We always see that they just export all their work into Word and then they keep working in Word, which again is great. At least they did some of their work online. And what's sad is that they pretty much lose of the some of the data-driven and web-based part of the work. So I have to say that there's a clear difference in the sort of in terms of adoption. We see a lot of younger people using it. Of course, younger people today are the people that are going to be older people tomorrow. So and I think that if you talk to any young scientist today, it seems like it's clear that the way that things are going to work in the future, it's more towards sharing and openness. So I mean, we're hoping, I think, that that's the direction that we're going to go towards.
Yeah, and I think in the context of Wikidata and Wikipedia, really we need to break down adoption into maybe 3 different buckets. Readership, contributions by our volunteer community, and expert contributions, right? So in terms of readership, everything that gets into Wikipedia, Wikidata gets distributed to monthly 500 million unique users based on our best estimates. In terms of the contributor base, the adoption, the community curating content on Wikidata, including this content, is around 7,000 people that we consider active in terms of completing at least 5 edits every month. And that's not as large as the English Wikipedia community, which is 3-4 times larger, but it's growing really, really quickly. And in terms of expert contribution, that's an interesting one. And I think Benjamin Good from the GeneWiki project has some really compelling arguments around the traditional model around biocuration, where you have soft money that goes into creation of a custom knowledge base that maybe is out for a couple of years. It's not integrated, it's kind of siloed, it's not integrated with other knowledge bases, it's great until it lasts. And then 5-10 years after it, it's gone. So all this public funding goes into something that cannot be easily reused. And one of the benefits you get for free by contributing Wikidata is that you get the persistency and distribution and scalability of infrastructure that you can use. So I think he has some really compelling points about adoption in terms of expert contributors to the system.
Thanks. We have time for one more question.
So this is actually maybe a little bit more of a challenge and kind of follows from what Dario was just saying. My name is Melissa Handel. I'm actually here on behalf of Force 11, but in another life. I'm a computational biologist, and I work on tools that integrate data from a large variety of sources for clinical utility. And we've been working with the Wikidata and with extracting data from the literature, and all the problems that all of you mentioned are problems for us as well. And I'm just curious as to, we have this real tension in terms of data quality and authority. So, I'm trying to figure out ways, how do I use the Wikidata, for example, in a clinical tool that has to be, CLIA certified and go through all of the IRB constraints and all these kinds of things. And so there's this real tension in terms of quality and provenance and what sort of authorities came to bless it in order to be used for such purposes. How much was it curated and by whom? And so I'm just wondering if all of you could kind of speak to how do we overcome some of these tensions in biology in order that we can have confidence in the data to be used in such a variety of applications. So there's something sort of pristine about our peer-reviewed literature that we want to move into this more open environment. And how do we do that?
Yeah, excellent question. So I guess this is one of the most critical issues for Wikidata. Wikidata is built from scratch with support for provenance and verifiability. So every single statement that you have in Wikidata, for example, gene ontology, like evidence codes from a gene ontology, they can be represented with a provenance, and in fact they should be, so that you can reconstruct where the information comes from. I think you're completely right about the fact that people should not cite Wikidata entry in the same way as Wikipedia can be cited as an entry point towards the literature. It's not Wikipedia itself, the authority about the information it contains. How to do that, how to make sure that we have full coverage and provenance is a technical and social challenge that we're currently trying to address. But in the context of like the GeneWiki project, for example, you will see that all the information is tagged with provenance explicitly. And even in the context of citations, we don't trust Crossref necessarily, we don't trust PubMed necessarily. So we want to make sure that every time when we ingest bibliographic metadata and citation information, even that data is represented with a provenance. So if you put it from Crossref, there will be an indication that that's where it comes from.
Yeah. So what I can say is that we haven't really dealt with peer review in a sort of in a proper manner. In terms of provenance, of course, we're very interested in that, and the solution that we've proposed up to now is very much technical. So I've talked already a lot about Git, and Git is also the solution to some of the provenance problems that we see. So since every single thing that you do to a document is tracked, whether it's like writing a paragraph or adding some data or replacing an image, you can see the history of a scholarly paper. So you can actually see like who did what in a paper. And that's all done from a very technical and very clean perspective. I know that there's some contributions to a scientific paper that cannot really be tracked by Git, such as brainstorming with your PhD advisor, for example, that is not tracked on Git. However, it's already like a great solution to allowing provenance. And in terms of like really using the analogy with Git and pushing it even further, I think that the idea of now I'm sorry if I'm being too technical, but in Git there's a thing called forking, which really means taking someone else's work and making a fork of it so that you build on top of it. I think that that's going to be, you did mention metrics, and I think that in terms of metrics, we're going to see things like forking, the number of times that your work was forked, for example. That's a very interesting, going to the future, way to not only reward the work that you did, and more than a citation. So I always say that I think that in the future, reusing someone else's research is going to be more important than citing someone else's research. So the idea is that I think that data reuse that is becoming more and more popular is going to have a technical solution to it, and I think it's really built on Git. That's my 2 cents.
Just to make a super quick pitch, speaking of provenance, is like crowdsourcing of where information comes from. Many of you will be familiar with Hypothesis, this open annotation framework that is being used by more and more organizations and communities to basically crowdsource the provenance, the accuracy of information. So, and I think that speaking of granular peer review at the statement level or figure level or tabular data level, that's really one of the best tools we have today. It's open source and it's supported by many publishers. So if you're not familiar with it, look into it.
And on that note, we need to break for lunch now. That was a fantastic session. Thank you all very much.